Welcome back to the 9th session of our Socket Programming in C laboratory series. And today will be about inter-process communications. So let's try to understand what are inter-process communications and why we need them. So basically, I've told you that we'll be creating processes, multiple child processes, so that multiple clients could talk with the same one single server at the same time simultaneously. And when we work with multiple processes, we will need to create such a thing, such a mechanism, so that the parent process could talk to the child processes to order to do something. For example, in order to provide that kind of mechanism, we will be using such thing called inter-process communication (IPC). So what this provides is a a mechanism which allows processes to communicate with each other and synchronize their data and actions. The communication between these processes can be seen as a method of cooperation between them. For example, a parent process might tell the child process to suspend its working for 5 seconds, or just stop working, or so on and so forth. Inter-process communication can be understood simply as a data transfer between two processes. So one of the examples of IPC is a pipe, a very simple example of pipe, and this presentation, today's laboratory series, will be about pipe, because I wanted to simplify as much as possible. So in order to create a pipe, what you need is just a simple array of file descriptor of size 2 and a function call called pipe. So let's try to understand what pipe is first. Pipe is simply a message exchanging means for processes. You can understand it as a stream between two processes. So that's why if you try to visualize it, it looks like a pipe. When the above function is called, the operating system creates a memory space that can be accessed together by different processes and returns the file descriptors used to access the space. It's basically a memory space between the two processes that can be accessed as a writable memory area from one process and readable memory area from a different process. So it's basically sending a message from one direction to another. And if you put another pipe here, that will mean message exchanging at the same time by both processes. So the file descriptor, as I told you a little bit earlier, the file descriptor must be an array of two integers, and the first element of that that array of file descriptors of size 2, the first element refers to the read end of the pipe, and then the second element refers to the write end of the pipe. That means if you try to write to this pipe, then you'll have to write to the file descriptor of the second element. And if you try to read from this pipe, that means you have to read from the file descriptor's first element. And so one of the simplest examples of pipe could be understood like this. You just create an integer array of file descriptors, it's as simple as that here, and then you make a function call to pipe and provide that array. After this, what operating system does is it creates a memory area and then maps it to these file descriptors and map them to the first element as an input and the second element as an output. And after this, what you could do is write to the first element of this file descriptor any message you want, and that will be read by another process using the zeros file descriptor inside the same array. So those set of two file descriptors will give us one single pipe. And this is one example. I will explain by looking at the code as well. If you try to compile and run, what you will be seeing is actually how the message is transferred from one process, one child process, to the another process and printed out. And let's try to take a look at the code and then try to compile and see the output of ourselves. And that is located inside the pipe1.c file. Let's try to copy and paste inside the CYGWin folder. and open the source file first of all. So here, like I told you, we are creating an array of 2 integers, which will be further used as a pipe, and then we are creating the message that will be transferred. And then we are creating a buffer as well for the receiving process to read. We don't actually have to create it here. We can go ahead and cut and paste it right here. And also the string message, we can put it here. It's just completely up to us. And then what we're doing is we're creating a pipe from this file descriptors on these file descriptors. And then we're creating a child process. And if we're inside the child process's scope, then what we're doing is we're creating the message and writing that message into this pipe file descriptors output stream, output file descriptor. And then if it's not the child process, that means it's a separate process. What we're doing is we are creating a buffer into which we will be loading the incoming data. The incoming data will be read on this first element of this file descriptor array. And we are making a read function call to that file descriptor and providing the buffer, and then after which we are printing out that message by using puts function call. So it's very simple, it looks very simple. So what we have to do is just compile and see the output. gcc-o pipe 1.c. If we run it, what we'll be seeing is that the message has been successfully transferred to another process. So this was a very simple example of how the pipes work. And moving on to the bad usage of the pipes, sometimes people try to use a single pipe to read and write by the same process at the same time. Pipes are not meant to be used bidirectionally, and if you want to use it bidirectionally, then you have to make sure that the timing does not overlap on the 2 processes, so that 2 processes should not be writing to the same pipe at the same time. And for that reason, what we usually do is we create separate 2 file descriptors, separate 2 pipes. If you want the 2 processes to communicate with each other at the same time, like bidirectionally, then when bidirectional communication is made using 1 pipe, timing of writing and reading data becomes very important. However, it's virtually impossible to control, so it's not considered as a proper bidirectional communication. The IPC pipe is not considered as a proper bidirectional communication. So this usage shows us the bad usage of the pipes bidirectional use. And here, as you can see, this is the child processes area scope, and this one is the parent processes scope. What child is trying to do is actually it's writing to the pipe and sleeping for 2 seconds and reading from that pipe. What it's doing is it's using both file descriptors of the same pipe. And what parent is doing is it's first reading the content from that buffer that the child has sent, and then it's writing. But there is a time, but there is no a time delay such as is in the child process, and that time delay might match and might not match, and that will be problematic because the read and write operations must have some logical sequence that must be completely matching in between those 2 processes, so that no data will be left inside the pipe buffers. And so that's why the pipes are not considered as a good bidirectional communication for processes. And moving on to good bidirectional communication, what we need to do is actually create 2 different pipes for both of which present one directional communication between 2 processes. So this is a good use where we are creating 2 pipes and calling pipe function on both of them, and then after creating them, what we're doing is we are writing inside, for example, the first child process scope. We are writing to the file descriptor 1's output, and we are reading from the file descriptor 2's input. So basically what we're doing is we're using separate pipes for writing and reading, for input and output routines. And we're doing the same thing in the parent process as well. We're reading from the file descriptor 1, which is shared to the write end of the child process, and we are writing to the read end of the child process. We are writing because it's an output. It's an output for us. The input end of the pipe for the child process is an output end for the parent process, and vice versa for the file descriptor 1. So as you can see, it's visually shown very easy to understand. So here file descriptor 1 is used to this direction, and file descriptor 2 is used the other direction. And if you compile and run, it will work all fine. And for a proper bidirectional communication, it is better to create two separate pipes, as in this example. Let's try to compile and run the pipe3.c file, which will be the correct bidirectional communication. In pipe 2 is, like I show you, the incorrect, invalid use of the... Oh, let's first just compile and run the invalid use of, I wouldn't say invalid, but like not accepted use of pipe, bidirectional use of pipe. Let's compile and run the pipe 2 first, and then pipe 3 first. gcc-o pipe2.c. So the parent process is actually printing out, and child process is also printing out the message, and it's working fine. But the thing is, like, it's working well because the time is somewhat matching, plus the logic is not very difficult. But when the logic gets really tough, for example, if this child process keeps writing, and then reading, and writing, if it becomes complex, and the same thing happens here, it might not be matching, and at the same time two processes might be overlapping each other. The actions of the two processes might overlap, like both might try to read, and if you put them both like trying to read, then what's going to happen? It will be just deadlock. It will be just both of the processes will be ending up waiting for each other. It will be just stuck. So stuff like this might happen, and this pipe will not be working fine. And instead what we do is we use the accepted use of pipes on bidirectional communication, which is the pipe 3 source code. So the pipe 3 source code, what it's doing is, as you can see, that it's also correct, because the logic was not difficult inside the pipe2.c file. It was still working, but it is not suggested by us to use, and by the other network developers as well. You should not use single pipe with bidirectional for bidirectional communications between processes, but instead you should use it like this way. We are creating two different pipes. We're creating the memory spaces and attaching to those file descriptors, and then we're writing to one file descriptor and reading from another, and we're reading from one and writing to another. So that's why this is a good way of using pipes to interact between different processes. And now what we'll be doing is we'll create a different source code, another source code, which I will also share between this, to show you how to really use pipes when you try to create a new source code. For example, let's call it a code.c file. What this code is going to be doing is simply it will create two child processes, and it will send a message to those child processes, and then it will wait for those child processes to finish. And I will also combine the zombie process as well, so that the parent process will clear up its child zombie processes. And after the message is sent to both children, the parent process will wait for those zombie children, and those zombie children, what they will do is they will read the message that's coming from the pipes from the parent process and print them out, and then just simply exit at the end when the parent says close. So let's just include first the required libraries, which will be usually stdio.h, unistd.h, string.h, signal.h, and syswait.h. So what we'll be doing is we'll jump to the main function and then create a PIDT. So what we wanted to do is actually we wanted to create two child processes. Create process. The first thing, like we wanted to create a child process, which will be the first child process. Let's call it child 1, and let's fork it here. And then if the ch1 is equal to 0, that will mean it's the child scope. Child 1 scope. Otherwise, it will be the parent scope, parent process scope. And what we want to do is we want to create another child inside the parent as well, so that there could be two children. Because what I said is like parent is going to be sending two messages to two children. We want to get it a little bit more complex, to the next level. And we're going to be checking ch2 is equal to 0. That means it's a child scope still, which is the second child scope. Otherwise, it will be the parent scope again. And now what I want to do is first, before forgetting to register to the signal of child process dying, I want to register a signal so that the parent process would be woken up when the child process terminates, and then the parent process will read its output, which is the example from the previous lab, but still I want to remind you a little bit because it might become a really important thing sometime in the future. So for that, what we need to do is we have to create a sig action structure, object from a sig action structure, and then set a handler to the sig action structure. So that will be the SA handler field of the structure. We have to set it to some function. For now, let's say the read read status. That's it. Let's call it just read status. This function will be created somewhere like above main, which will be just simply a void function, and which we will fill later. And then what we have to do is we have to first make a sig empty set function call to the this structure's mask, and that has to be converted to an address so that the set must be like emptied out. And then we have to set the flags to 0. And then we have to register this variable that we just created to a signal function call with sig child, and providing the address to this structure and saying just nothing extra. So now we're done by registering the signal, and now here let's try to read the status code and clear our zombie process. Okay, read zombie child status code. For that we need the status variable first of all, and then we have to actually get the child process's PID. The child process, let's just call it CH, that's it. Wait PID any child with this status without stopping, because we're sure that the child has already terminated, so we don't have to hang it. And then what we're going to be checking is if exited, really the processor has exited, then printf that process this terminated with status code, let's call it child process this terminated with status code of this. So the first argument is not actually string, it will be decimal. The child process with PID this. PID is the process ID that we just got here, CH, and then the status code is actually this one, but terminated to a wrapped up around the macro of exit status and providing the status value of the status. So here we are done with by clearing out the zombie process. We don't have to worry about the zombie process anymore. So when we can move on to creation of IPCs. So for this first child process, what we need to do is we have to create an IPC. Create the first process plus IPC. Let's call IPC 1. This will be the interprocess communication 1, and here it will be interprocess communication 2. Create. Oh, let's just copy this comment. Put it here. Create second child process plus IPC2. So when we create a first child process, what we want to do is, so let me just put it here too, just in case. So when we create this child process, we already duplicate this memory area, and before it, what we want to do is we want to create the pipe so that we could be able to, we were able to talk with this child process after this line. And before this line, what we have to do is we have to say, for example, FDS1, that will be the first file descriptor, the first pipe that will be talking, that will be used for interaction between the parent process and the first child process. That will be containing 2 integers, and that will be converting it to a memory area using this function call. And that is it. Very simple. So we just created a pipe after this, and we can just copy and paste this one right here before creating the second child, and then saying oops, here it's 1, here it's 2. I just made a slight mistake. It was FDS. Instead of this, it should be FDS1. And here it should be FDS2. So here it is also done. We've created a second pipe for the second child process. And what we will be doing here is actually very simple. The child 1 process is what it's going to be doing is it's going to be reading the message that will be coming from the parent process using this file descriptor. And for that, let's create an extra function, external function right here, so that the content of this child will be handled right there. It will be something like this: handle child1, and provide this FDS1 here, so that the function would know which pipe it should use to interact with the parent process, and then print out like. And then also let's just in order to know what was the exit status code difference between the two child processes, let's also provide 2 different exit codes as an argument to the let's not call it handle ch1, but just child process. And let's just provide the exit status code as an argument here too. Let's call just 32 for the first child, and let's call the same thing for the second child, but saying use FDS2 plus the exit code of, I don't know, like any value 612. And what the parent process is going to be doing is not defined yes, so fill later. Let's fill the child processes function first, which will be this function, void handle child process, which will be accepting an argument of integer FDS. FDS is basically the pipe, and the exit of status code, let's say, or exit code, I don't know, it's completely up to you how to name it. And then so goal of this function is to read message from FDS, and then when, for example, let's say dot is in the message, terminate with exit code. So that's the goal of this function, so let's try to implement it. For that, what we need to do is actually we have to read each character, the message that's coming from the parent process character by character, so that we could detect the dot. For that, let's say character C will be the buffer for our input and output operations. And here what we'll be doing is while, let's say, reading from the FDS0, which is the parameter that was provided to this function, and storing it into this variable's address, just after reading 1 byte into this one, because character is 1 byte, is greater than 0, that means it was successfully read. If this function call returned some value like greater than 0, then what we need to do is actually we have to print f, but instead of printing f first, we have to check if it was dot, because in case of dot we have to terminate it, right? What we could do is actually put an end case here, so that like after reading you would check that the value of c is not equal to dot. That's the first option, is not equal to dot, and then just make a printf function call, and then just put a value of, for example, no, instead of this one, sorry, I made a mistake. Instead of this one, just say I want to print out this character and provide the character variable right here, and then after all of this, that means either the message hasn't been received by the child process, or the message has been received and the message is the dot character. So you can be just keeping on receiving the correct letters. For example, hello world, HELLOWORLD, and then at the end there is a dot, right? And then so this will make it false, and then the while loop will break out. At this point, what we have to do is we have to exit with an exit code that was provided to this function. So that was the goal of this whole function, and that's very simple, right? If you just remove it, it will be simply 4 lines of code. So that is it for the child process to do, and the goal of the parent process is actually just to send 2 different messages to the child processes and just to sleep for a while, so that the parent process would print out the terminations of these 2 children, and voila, that's it. So let's do those things. First of all, for that, what we need is actually we need a message. The message would be, for example, let's say hi to child 1. Let's say hi to child 1, at the end put dot. That means this dot is going to be terminating, ending the life of the first child process. And then let's send it right to FDS1, 1, and remember 1 is the output end of the pipe 1, so we're sending to the child 1 this message, because we just said child 1, MSG and strlen of MSG, and strlen is just the length of this string. Just send this many bytes of this buffer to this file descriptor. That is it. And after this, let's change MSG to, for example, 안녕 to child 2. Let's put an end to the life of the child 2 as well. Right, FDS2, in this case, MSG of strlen of MSG. That was very simple, it wasn't very difficult, right? Inside the parent process scope, send messages to children. So that was the task of the parent process, first of all, and then wait, just like zombie, let's just call it zombie, and then just for that we need to just sleep for a while, that's all, we don't need to do anything extra. And then after this, let's exit with a successful exit code of 0. We don't actually have to write it, but just in case, like, by the way, this one is also optional, this one is also optional, just I'm writing just in case to show you that the zombie processors are being successfully handled in this code. Let's try to compile and run this code, so that like we know that we understand how this code is built and how it works. Let's compile and run it. GCC code -o code code.c. Oops, I just made a slight mistake. Signal. I made a mistake inside this signal. Oh, sorry. It's not signal, it's sig action. First is that issue. I think it should resolve the issues. Nope. Oops, it's not an error, but let's try to remove this one as well, because stdlib is also a very important library. It's almost always used, but I forgot to put it. It's not an error, but still, it's a warning. So let's get those warnings removed and compile that source file and run it one more time. So now we can oops, let me print out new lines as well, because it is very ugly. After having finished printing out the message on the child process, let's put a new line here too, so that it could look decent, because now it doesn't. No, we don't even have the new line here. We could just put it here. Why didn't I do it? Okay, so let's just forget about this printf \n stuff. So let's just put it here, and that will have the desired output for us, the clean and tidy output for us, and after which we will be seeing how the zombie children are dying, also how the message is being transferred between the parent process and the two child processes. Let's run it, and we can see that the messages are being delivered out of order, and that is not always assured. They cannot be assured. It will change sometime. The child 1 will receive it first, sometime the child 2 will receive it first. But anyway, the fact is that both of the children are working properly. And then the child process are terminating with an exit code of 32 and exit code of 100. That 100 should not have been there, because we have provided, I think, 600 something value. Let's try to change. I'm not sure why that was like that kind of weird issue. Let's try to compile it again and run it. Now it's 12. Maybe the value was like overloading. So the thing is, the point is, sometimes this code will be in this order, like child 2 will be printing first and child 1 will be printing second, and sometimes the child 1 will be printing first and child 2 will be printing second. And that's the exact reason why you should not be using pipes as a bidirectional means of communication between processes, because the timing is not guaranteed to be in your expected order. So therefore you have to create two different pipes if you want to make bidirectional communication between processes. Thank you for paying attention. This was it. Oh, yeah, there was one more example that I just forgot. Let me just cover this one as well, and that will be for sure it. So this is the last slide. The IPC Echo Store Server C. This is one of the use cases of how inter-process communication could be used inside a networking application. And we remember, for sure, that the Echo Client and Echo Server, like right here, the Echo Client and Echo Server was giving us this kind of behavior, like the gcc-o echo stores server gcc-o client echo client. The behavior was the client was sending a message. Oops, I made a mistake. The client was sending a message, and the server was making that message bounce back so that the client would receive its own message. So that's why it was called echo, right? How the inter-process communication could be integrated to such an application. It could be, let me just delete this leftover first, and then I will move on to explaining more. Come on. Okay. So it could be in case, for example, the echo server, before sending back those messages, it might want to also store it, right? And the server could have created a separate process that will be storing those messages, but when the message comes, the server must be able to inform that process to tell that the message has been received on the server side. And that event occurs in an undefined undefined point of time. That means whenever a client sends a message, at that point, save this message. So that means the process inside the TCP echo server has to, the two child and parent processes have to communicate with each other, so that in case of an incoming message occurs, then the child process has to store that inside a file. So what we're doing is like one child process that keeps receiving messages and storing them inside a file, and another process that keeps sending messages to the Echo client server. So we are reading the message and writing to two different ends, which is one of them is the client socket and second is the pipe. So that the another child process could, I made a mistake, sorry. Oh no, I didn't make a mistake. It's alright. It's alright. So this one is also a child process. This one is also a child process. Two child processes are interacting with each other with a pipe. So this child process is informing the another child process that a message has been received from a client, and it's asking for the second child process to store it by just making write function call, and it's writing to that pipe, and the second child process is simply reading from that pipe FDS, and then it's storing inside a file. Fwrite means writing into a file pointer, and then it's doing it after 10 messages are received. So it's basically storing 10 messages, and that's it. And then it's just closing that child process. So let's go ahead and compile this file, and that will be it for today. So this is the example of Echo Client and Echo Store Server, which I have just run, but I didn't show you how it is storing those as a file, the messages as a file. So now that part is the interesting part. So the store server is creating a child process right here, and this child process is actually just waiting for the pipe, and then whatever that comes through the pipe, it's writing down as a file 10 times, and then it's closing. And it's also creating another different child that will be reading and writing back to two different ends, which are one of them which is the client socket and the second is the pipe. So now that I have just shown how the Echo Store server is written, the echo client.c file is just the simple echo client file that connects and sends and terminates if a client if the person enters Q from the keyboard. Let's just go ahead and compile those two source files and see the output again. gcc-o server echo store server gcc-o client echo client.c file. Server will be running on port 4444. The client will be running on. So now that we're connected, let's send 10 messages. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The child process that was used for writing files has been removed. That zombie process has been removed. Let's try to exit it now. That part is also done. Apologize. So the echo message.txt contains the 10 messages that we just sent, and voila, that was what I wanted to show you for today. Thank you for your attention. I hope the lab sessions are not very difficult for you, and if they are, please don't hesitate to email me to make any kind of suggestions. Thank you so much, and good luck.